Okay.
Okay. So earlier we got to most of section 7.2 today. I'm just picking up where we left off. Basically, the critical thing I showed you was that if we define a linear transformation on the basis, then that uniquely defines a linear transformation for the rest of the vector space, which is a really nice thing to know. We'll be using that in the future section, so I'm not going to give you examples just yet. The next definition, which is important, maybe it's the most important definition in the whole semester, I don't know. Here it is though. Let V and W be vector spaces. Okay. Then we say V, and we draw squiggly arrows like this, which means that V and W are isomorphic. So what's it take for V and W to be isomorphic? If there exists some linear transformation L from V to W, again a linear transformation which is a bijection. Okay. So you might notice that it suffices to check that L is linear and invertible because we have theorem 7.2.14, which I didn't actually cover in class, sorry, which shows that the linearity of L inverse follows for free. So if we just show that the mapping is linear and it's invertible, linearity of the inverse follows for free in our context. Again, you need to read the rest of section 7.2. I've covered most of it in class, but there's a little bit I missed. All right, so here's the theorem. Oh, use a different color. So one important theorem is that if you have two vector spaces which are isomorphic, it follows that they have the same dimension. So here it is. Theorem V isomorphic to W, then dimension of V equals to the dimension of W. I suppose as a precondition here, I'm assuming that the dimension of V and the dimension of W is less than infinity. I suppose it probably suffices to assume one of those things because you can't have a bijection between an infinite dimensional space and a finite dimensional space anyway. But that said, here it is. So let's there we go. All right, so let L from V to W be a linear bijection as we're assuming exists. All right. Suppose beta equals to V1 Vn is basis for V. Right? Then notice that the image of beta, so L of V1, L of Vn, is a linearly independent subset of W. Why is that? Well, we said that L is a bijection, right? We just proved a little bit earlier in this section that if the linear transformation is an injective mapping, that it maps linearly independent sets to linearly independent sets. Of course, beta is a linearly independent set. So the image of beta under L is, again, a linearly independent set. Okay, what else? Well, also, let's see here. If W is in W, little w, then let's see here, W is equal to a sum of, what is it? I don't know. J equals 1 to, oh, curses. Not sure I want to go that direction. We need to use the mapping surjective somehow to get that this. Oh right, I'm making this harder than it needs to be. Erase that. Okay, so. Oh yeah. So let W be an element of big W, then L inverse of W, and we can, I mean, it's an invertible mapping, right? It's a bijection, which means it's invertible. In particular, so we can calculate the inverse image under the inverse mapping of W. And that is an element of what? V. Yeah, that's an element of V. Hence, L inverse of W is equal to the sum, let's see here, I equals 1 to n of some numbers, let's call them C. C sub I was V sub I, right? Mm-hmm. And so that implies then that W is equal to L of that, right? But we can use the thing we proved earlier today to bring the summation out, because it's linear transformation. Remember, we proved that by induction earlier. Right? Mm-hmm. And that is exactly something in the span of L of beta. Right? Mm-hmm. So in other words, this L of beta is a generating set for W. Anything in W is hit by the span of this. Hence, L of beta is basis for W, and so the number of things in beta is equal to the number of things in L of beta. So therefore, the dimension of V is equal to the dimension of W, as I claimed. Okay. There. I got, apparently I have not drank enough coffee just yet. Okay. Now this theorem has a converse, however, I need a proposition before I prove the other half. So let's see, next theorem. Try to get on with it. Don't want this to take too long, I still got other things to show you today. Okay, so proposition 7.2.20, we've got if T is a mapping from vector space V to vector space U, and S is a mapping from U to W. Actually, these aren't just any mappings. I'm assuming that these are isomorphisms. Guess what? If those are isomorphisms, then S composed with T is an isomorphism. Moreover, and this is the interesting part, vector space isomorphism is an equivalence relation. All right. So, let's see here. What does it take for us to prove that S composed with T is an isomorphism? We need the composite's a linear mapping, right? But we've argued that previously, so we'll dispense with that. So notice the composite is in fact a linear map from, let's see here, T starts with V, you go to U, you go to U, you go to W. So we go from V to W, right? So it is a linear transformation because it's a composite of linear transformations. Let's see here. Let's show it's injective. So suppose S composed with T of X is equal to S composed with T of Y. We were trying to show that X is equal to Y. So if that's true, that means that S of T of X is equal to S of T of Y. Right? Hey, but these are isomorphisms, right? So they're inverses. Inverse functions exist.
Mm-hmm.
So we can just operate by S inverse on both sides. S inverse of S of T of X is equal to S inverse of S of T of Y, which tells me what? That tells me that T of X is equal to T of Y. But then T is also an isomorphism, right? So it has an inverse mapping. So T inverse of T of X is equal to T inverse of isomorphism. Really easy to work with. So we get X equal to Y. Thus, S composed with T is injective. It's 1-to-1. All right. So that's half of it. Now what else do we need to show? I also need to show that S composed with T is a surjection, right?
Mm-hmm.
So to do that, I'm going to erase this and put it right here again. You guys can pause and write if you want to. I'm just going to...
Oh, just keep it.
What's that?
Just keep it.
Oh, no, you can just... talking to...
Talking to them. To audience.
Oh, yeah.
Yeah.
It's okay. I guess you're part of the audience.
Yeah.
So, the next half of the proof is surjectivity. So we should let W be an element of W, right? And we want, what do we want? We want to find X an element of V such that what? S of T of X is equal to W.
Mm-hmm.
But basically you can just solve this for X. So X is equal to, first you take S inverse,
T inverse.
yeah, and T inverse. And so we can try that. That's definitely a point to use. So this is a parenthetical comment. This isn't actually part of the proof. Okay, so this is we put a box around it. This is scratch work, but I suppose it's not bad to show you it. You know, if I wanted to just be correct and lose all of you, I should say we consider S composed with T acting on T inverse of S inverse of W. All right?
Mm-hmm.
And so you just do it. So that's S of T inverse of S inverse of W. Okay.
Okay.
So, first of all, T composed with T inverse gives you back whatever the input is, so that's S of S inverse of W by definition of inverse of T.
Mm-hmm.
And then that's just W again by definition of inverse of S.
Mm-hmm.
Aha! But that suffices to show that S composed with T is onto W, or it's a surjection onto W, so. Because I've just shown that an arbitrary element of W is reached by a specific choice of something in the domain. Now, so then we have that S composed with T is a linear transformation,
Mm-hmm.
which is an injection and a surjection, which means it's a bijection, which then means by definition it's an isomorphism. Check. All right, so we've done the unexciting part of this proof now. Now I'm going to move on to the last sentence in proposition 7.7.
Where's the homomorphism?
What's that?
Homomorphism.
Homomorphism?
Mm-hmm.
Oh, well, I'm not talking about homomorphisms just at the moment. I'm just interested in isomorphism right now.
Okay.
But you know, homomorphism is, I guess it's interesting, but I mean, anytime you have a linear transformation between, you know, one vector space and another, that gives you a homomorphism. It's just that finite dimensional vector spaces are homomorphic. So it's a little bit less exciting. I mean, when you have a homomorphism between groups, it's kind of more exciting because there's lots of finite dimensional groups which are not homomorphic, right? But can you always write a linear transformation from one vector space to another? Supposing we're working over characteristic 0. Yeah, I can write a linear transformation form. I mean, they're homomorphism is it's so everywhere. It's hard to appreciate, I think.
Mm.
That's one big contrast between this and, say, elementary group theory. Okay, enough about 421. Back to 321 again. Okay, so equivalence relation. What does it take to show equivalence relation? So first of all, I have to show that a vector space is isomorphic to itself. So how can I show that? Is true, as you can look at the identity transformation, id v mapping from v to v. This is, so id v, if you haven't, I don't think we talked about it before, but id v of x is just equal to x for all x in v. So it's just that, it's the mapping, it's a very, very simple, boring map on the vector space to itself. It's the identity transformation. It's simple to check that this is onto, it's one-to-one, it's certainly invertible, it's its own inverse,
Mm-hmm.
and it's a mapping from v to v. This shows that v is isomorphic to itself, therefore isomorphism is reflexive. So that's a third of the battle. What's next? We need to show symmetric, right?
Mm-hmm.
So suppose that v is isomorphic to w, and suppose that phi is the isomorphism, right?
Okay.
Then
I want to show.
I can just look at the inverse.
Mm-hmm.
Okay, the inverse, which would go from w to v,
Mm-hmm.
is a linear transformation.
Mm-hmm.
There's a theorem earlier in this section which proves that for sure.
Mm-hmm.
Because if you have a bijection which is linear, the inverse is automatically linear.
Mm-hmm.
So that's an isomorphism of w to v.
Mm-hmm.
So
Implies W is somewhat to V.
right. So in other words, the isomorphism is symmetric.
Mm-hmm.
Right.
Mm-hmm.
And then finally, the other thing here, we just proved that the composition of isomorphisms is an isomorphism.
Mm-hmm.
So the transitive really needs that. If I have, let's say v
Isomorphic.
is isomorphic to u, and u
Isomorphic to W.
isomorphic to w, and say that this is isomorphic under with the isomorphism t, and this is isomorphism s, then S composed with T
Mm-hmm.
is a isomorphism from
From V to W.
yeah, from V to W by a proposition.
Mm-hmm.
The first part of the proposition above, and therefore V is isomorphic to W. So that shows that if V is isomorphic to U and U is isomorphic to W, that implies V is importantly isomorphic to W,
Mm-hmm.
which goes to show you that the isomorphism is transitive. Now this is pretty awesome because what this means is that if we think about the set of all possible vector spaces, we can partition it into these classes of isomorphic vector spaces, and you know, you give me two, they're either isomorphic or they're not, and there's a whole bunch of other ones that are isomorphic. Now, obviously, whenever you have an equivalence relation, you can partition some larger set into a bunch of disjoint subsets. It's nice to be able to find some sort of like standard representative for each element of the partition, and that's where our next theorem goes. Oops, where'd it go? Aw. Schnikes. Well, I guess I did actually the converse of the other thing I was doing. I was thinking of going a different direction just now, but let me erase this.
Mm-hmm.
There's kind of two obvious things to say here. All right, so where was I? Fine, I'll stick with the notes. Theorem 7.2. 2.21 says let the dimension of V and dimension of W be less than infinity, finite dimensional, then V isomorphic to W if and only if the dimension of V is equal to the dimension of W. All right, so theorem 19 already established this direction of the proof. So this direction was theorem 7.2.19. So we'll just concern ourselves with the converse direction now. So assume that the dimension of V is equal to the dimension of W, okay? And let's set that equal to n. This actually brings us into my next section. And the thing I was about to talk about anyway. So what I'm going to do is draw a picture here. So if the dimension of V and dimension of W being the same, it means that both of them have what? They've got a basis with n things in it, right? So I'm going to let V have basis beta, V1 through Vn, and I'll let W have basis gamma, and let's say W1 through Wn. I want to find an isomorphism between these worlds, all right? So instead of attacking it directly, what I do, I suppose, well, fine, I guess I could see a direct way to do it, but I'm going to, now that I look at it, all of a sudden I see a direct way to do it, but let me not do that. So what we're talking about in the next section for the most part is this idea of a coordinate map, all right? So the coordinate map takes you from the vector space V down to, since we're keeping it real, Rn. And so that's the beta coordinate map, all right? And on the other side of things, we have the gamma coordinate map, all right? And so, again, Rn, you could identify these as being the same. I could even use the same copy of Rn if I wanted to. I'm just drawing them separate for certain reasons later. And the definition of phi beta is just this. Phi beta of Vi is equal to Ei. All right? And over here, likewise, phi gamma of Wi is just equal to Ei, where these are the, this is the span of E1 standard basis, right? Likewise over here. So for me, one sort of natural way to get an isomorphism from V and W is to just kind of, well, I use the identity mapping, which is kind of silly. It's kind of silly, identity mapping at Rn. But if you just kind of follow the diagram here, like so, that will give me a mapping here in the following sense. So this orange map would be what? I would take, I start with phi beta, I compose with the identity, which I won't bother writing.
Compose with phi gamma.
Phi gamma inverse, right? See, this if phi gamma goes this way, then this would be phi gamma inverse. So basically, this map up here, the one that I'm going to propose as an isomorphism, I can just say L equals to the inverse of the gamma coordinate map and the beta map. This is a linear map because it's the composition. All right, so by the way, the coordinate maps, and we'll prove this in gory detail in the next section, coordinate maps are themselves isomorphisms, okay? So because these maps are isomorphisms, that's actually pretty easy to choose. The phi gamma and the phi beta, these are isomorphisms. It follows that their composition, the inverse is also an isomorphism, that their composition is again an isomorphism. So L is an isomorphism from V to W, and I believe that's what we were trying to show. So that's about all I have to say for section 7.2, so we'll cut it off right there.
And go cool. Okay, that's good.
Okay.
So stop.
Yeah.